Day 51, page 583, Thermodynamics, number 28. Here I've drawn the diagram as indicated. We have an ideal gas that's starting at a volume of 20 liters and converted to meters cubed. That should be 10 to the negative third. I've converted up here in the upper right the pressure in atmospheres into newtons per square meter, which is a Pascal, up in the upper right up here. So this is the pressure we're talking about. And then 20 liters, which is 20 decimeters cubed. And to go from decimeters to meters, you divide by 10, but since you're going from decimeters cubed to meters cubed, you divide by 10 3 times. So in essence, you move the decimal over 3 places to the right, and you get this many meters cubed to start with. Compressing it into 2 liters, so with the same type of conversion, you get 0.002 cubic meters of gas at the end. It's quite a compression, and you can kind of relate to 2 liters. You know how big 2 liters is, like a 2 liter volume of pop. You know how big that is. So you went from point A to point B along this process, and that's when the work is being done on the gas. That'll be considered positive. From B to C, there's no work done on the gas. There's no area under that process, that line that I'm indicating right there, and you end up at the same temperature that you started with on the same isothermal line. So there's the diagram with all the units converted into standard units. And so we're just looking at the work done from A to B. And the equation is, the work is technically, if you want to follow all the sign conventions, negative P delta V. Constant pressure of 3.03 times 10 to the fifth newtons per square meter, pascals. And the change in volume is a negative. It's a loss in volume of negative 0.018 cubic meters. So that's how you get, when you take two negatives and you multiply them, you get a positive answer. To be consistent with our convention that work being done on the gas is positive, because some external agent is compressing this and putting energy into the gas. So that's the work from A to B. But that's also the net work done, because there's no work from B to C. Now in part B of this problem, okay, this was the answer to part A. They don't really delineate A and B, but then they also ask you, what's the net heat flow for the entire process? So in part B, we're going to use delta U total, or net, equals Q total, or net, plus the work total, or net, for the entire two-step process. Well, delta U total is going to be 0 because the gas ends up at the same temperature it started with. So point A and point C are at the same temperature, therefore the delta U is 0. So we have 0 over here. And we know that, well, we're looking for Q total. We don't know that. But we do know that the work total is the 5,450, because there's no work from B to C. So the only work done is from A to B. So that's, once again, following convention, it's positive 5,450 joules. So that just tells you that the net heat flow is going to be negative 5,450. So in other words, there's going to be heat flowing out of this gas, Q total. Net heat flow is negative 5,450 joules. Now, I think from point A to point B, there's actually, well, heat flowing out of this gas, actually more than that. And from B to C, there's actually heat flowing into the gas. You could double check that with our isobaric process from A to B and isochoric process from B to C. But that's the negative 5,450 is the net amount of heat flowing out of the gas. Like I say, more heat flowing out of the gas from A to B, but heat actually entering the gas from B to C for a net of negative 5,450 joules.